Thank you, Compasso, and the organizers for the invitation to speak at this school. It's really a great pleasure to see so many young people interested in learning about this subject and to be joined by so many other distinguished lecturers. Please feel free to raise your hand to interrupt as we go along. Happy to work stuff out on the side. So Anne talked about this new paradigm for physics, quantum mechanics, which leads to a new paradigm for computation, quantum computation. This means we need a new kind of algorithm to take advantage of this additional power offered by quantum computation, that we believe is offered by quantum computation. And here's a picture of a few of the current recent implementations of quantum bits. These four little loops, 1, 2, 3, 4, these are known as superconducting qubits, and the wiggly lines are ways for these two qubits to interact. So you can do two qubit logic, where pairs of qubits interact. Over here we see a gold chip, which is a two-dimensional ion trap. So you can trap ions on the surface of this chip and do small quantum computations there. This thing in the middle is a sort of a cartoon of the longer-term vision of what we could do with ion traps, for example. So you have small arrays of ions where you could do logic. In separate arrays, we can control things pretty well, and then we have to find ways to communicate or interact between these small traps and implement large-scale quantum computations. So what kind of computing model do we tend to work in? Well, the most popular one in which we describe our quantum algorithms is the quantum circuit model. It's very closely tied to the underlying physical system. You can see a relatively close connection between the two. Whereas with classical computation over the recent decades, we've now very much abstracted the programming layer from the physical layer. But this is the very early days of quantum computing, so it's very natural that our computing model very closely reflects the underlying devices. So let me define, and Anne already has, but let me sort of repeat the definition of the quantum circuit model. I'd like to start with a reversible computing model. It's very often, some people will say, look, quantum computing is so different from classical computing. And they'll pick a definition of classical computing and a definition of quantum computing, so they're maximally far apart. So I'm going to do the reverse and come up with a definition of a classical computer and a definition of a quantum computer, so they're, I think, as close to each other as you can get. So reversible computation is a model of classical computation where, apologize, some of the font, the zero got a bit, letters got a bit distorted, but hopefully you can make it out. So this is known as a controlled NOT gate, right? Or Toffoli gate, for Tom Toffoli. It flips the top bit if and only if the two control bits, in this case the bottom two bits, are both 1. So in other words, if A and B are both 1, then you flip the top bit. The net effect is to compute the AND, the logical AND of the bits A and B. And if we discard the two input bits, and if we treat that input 0, so we initialize the top bit to 0, so the top bit encodes the AND of A and B, we've implemented, this is a way of implementing the AND gate. So on the right-hand side is sort of the traditional AND gate you'll see in computer logic. And on the left-hand side is a reversible implementation of it, where we have to add in a bit of extra workspace. We have to discard some of the answers, but we can achieve this way the AND gate. So if you give me an arbitrary circuit that is not reversible, right? So you take the AND of the first two bits and put the NOT of the third bit into that, together with that answer, and take the NOT of that, and so on. You compute some bit D. You can compute the same circuit reversibly. So, and you can even recover all the input bits. But the net effect is you start off with the inputs and some workspace, you compute the answer, and with very little effort you can recover all the input bits as well. The bottom line, the only point I'm trying to make right now is that we don't lose generality by restricting to reversible circuits. So for reasons I'll elaborate on later, it's actually very convenient to think about reversible circuits. But I can, without loss of generality, define my classical computer as a reversible computer. Now how might I implement this reversible computer, a small instance of it, say? I need some two-state system. I need a bit of some sort. So let's just imagine my bit is an atom, and 0 means this electrons in the ground state, and 1 is the electrons in some excited state. And with a laser pulse, whose frequency is tuned to the energy gap between ground and excited, I can drive the atom from 0 to 1 and 1 to 0. And I can do it in a way where I don't actually have to look at the internal state and know whether it was a 0 going to a 1 or a 1 going to a 0. So with negligible leakage of information or negligible coupling in the environment, I can implement a NOT gate in this bit. For now, this is just a classical bit, and NOT is definitely a reversible operation, it's its own inverse. And there are sequences of interactions where you can flip the second bit if and only if the first bit is in the state 1, for example. People have demonstrated these kinds of experiments. This is a way of implementing what's known as a controlled NOT. So if the control bit is 1, you flip the second bit. And so on. And this can be done with negligible coupling with the environment. So you don't have to heavy-handedly look at the atom, figure out if the first thing was a 1, and if it was, then apply a NOT gate to the second bit. You can do that, but it's sort of a slicker, less invasive, intrusive way to do it is there's a very gentle sequence of pulses one can apply that does this operation without leaking to the external world whether the control bit was a 1 or a 0, or the target bit was a 1 or a 0. You can actually do this. And so a reversible computation to initialize a sequence of bits and apply a sequence of these pulses and implement a reversible circuit. This is not a quantum computer yet. It's just a very, very small reversible computer that is sort of minimally wasteful or minimally interacting with the environment. Now, you could ask, is this a realistic way? Could you really build a large classical computer this way? Well, the first thing you would say is, well, even if this is error-prone, if the rate of errors is below some reasonable threshold, we can apply classical error correction methods to this. Well, let's not do that yet. Because if we worry about doing it too soon, is we might be heavy-handed in how we do this. We might say, well, let's just look at these bits and compute some syndromes and correct it and so on. We might extract more information than we really need to. So before we worry about stabilizing these systems, let's see if we can get more out of such a computer. So again, I've been describing a classical reversible computer, but it's living in a quantum. It's actually living in a quantum paradigm, which tells us that any physical medium capable of representing a 0 or a 1 can actually represent a state, can actually be in a state described by a linear combination of 0 and 1, as Anne told us earlier this morning. So alpha 0, 0 is alpha 1, 1. Where these alphas are quantum probability amplitudes. So if we use this principle, this is again the same physical system, except remember that NOT gate, which is also known as a pi pulse, apply it for half of the time. It has to do something. It has to leave your physical system in some state. And the state it leaves it in is in fact the superposition of 0 and 1. Without loss of generality, we can assume it's 1 over root 2, 0 plus I over root 2, 1 if it started off in the 0 state, and if it started off in the 1 state, it goes to I over root 2, 0 plus 1 over root 2, 1. If you apply this pulse twice, you get a NOT gate, also known as an X gate, up to global phase. There's lots of reasons why it has to be more or less something like this. It's something which in the intermediate state, if you were to measure, gives non-deterministic answers. But if you apply it twice, you get a deterministic answer. It's a very puzzling thing. But this is actually what's known as a pure state. So it's actually a definite state. If you apply this pulse twice, you get a definite state, which is the opposite of the input state. So if you add this gate, and again, we didn't need new hardware. It was just use that same control hardware you had before, the same lasers, except apply half of the pulse. And you get this gate. And that captures the power of computation in a quantum paradigm. This quantum circuit model, which consists of reversible classical gates, sufficiently powerful reversible classical gates, together with things like the square root of x gate, gives you the full power of quantum computation. By full power, I mean it gives us what's known as a reversible a universal quantum computer. So a computer, so these circuits built out of a set of gates. So you take a set of gates and you glue them together into some array, a network of gates or a circuit of gates. That set of gates is said to be universal if for any positive integer n, you give me an n-qubit unitary, and then there exists a circuit that approximates that unitary with arbitrarily low error. So for any epsilon, there's a circuit on n qubits made out of those gates that gives you an epsilon approximation of that unitary. And that's the best we could realistically hope for, because unitaries, there's uncountably many of them. And if we want to build them out of a finite number of building blocks, we can only ever approximate them arbitrarily well. So it needs to be universal. So if you can do anything, if you can implement any unitary, you can implement the unitaries and describe that create entanglement. So a necessary condition for a universal set of gates is that they enable the creation of entanglement from non-entangled states. So we call it 2-qubit gate entangling if for some product state, so two uncorrelated qubit states, it produces an entangled state. This is a minimal condition in order to achieve universality. You have to be able to create entanglement. It turns out that if you give me just one 2-qubit entangling gate, together with all the 1-qubit gates, then you have universality. So it just takes one entangling gate, plus the ability to do any 1-qubit computation. Now this is an overkill, because we don't need to we never ask for the ability to exactly implement any unitary, and we certainly don't want a computing model where you have an infinite number of gates that you can build your circuits out of. We want some simple, finite set of building blocks, and we focus on building them very well. But it's a starting point, so as long as we can approximate all the 1-qubit gates arbitrarily well, then that's good enough. So can we achieve universality with a finite set of gates? Yes. And so one of the most well-known examples, and most used examples, is the Hadamard, the T gate, and the controlled NOT gate. The controlled NOT gate's entangling, and the Hadamard and the T gate is a phase gate. Pi over 4 phase. This is universal. The Hadamards and T's give you a dense, arbitrary sequences of alternating Hadamards and T's, or powers of T's, give you a dense subset of the 1-qubit gates, and then together with the entangling gate controlled NOT, you achieve universality. These gates also have a wonderful property that you can implement them fault tolerantly. And I'll tell you a little bit about fault tolerance today, but it's not a major focus of this school. So this is universal in the sense that I defined earlier. So it suffices to build these 3 gates. And you can think of a high-level quantum algorithm, you can compile it down to a circuit made out of these 3 gates. It's important to note that most quantum algorithms, the ones we're going to talk about during this school, are not designed to be run directly on these noisy physical qubits that I showed you on my first slide. Because, at least for the foreseeable future, our physical qubits are going to be much noisier than the classical qubit, the classical bits we use today in our processors, in our computers. So we're going to need some error correction on top of these physical qubits to achieve essentially noise-free logical qubits. Right, for most of this school, we're going to be working at the logical layer. I'm going to design circuits of controlled NOTs, T's, Hadamards, and many of the other gates. And I'm just going to assume these are error-free. Of course, you'll not be surprised to learn that the qubits we're implementing in the lab today are far from error-free. They're not so bad, actually. They're 99.9, 99.999, sometimes even more nines. Those are the kind of fidelities that are being achieved today. But to implement an algorithm with 1 billion logic gates, even a 1 in a billion error rate is not enough. And we're not achieving a 1 in a billion error rate in everything. We're getting close to 1% error rates, even less, in some of the operations. And there's others which we can do with several orders of magnitude better precision. But what's the worst performing operation? It's on the order, typically in the order of 1% to 0.1%. So most of our algorithms are going to talk about the logical layer. The physical layer, what's going to happen, the connection between the physical layer and logical layer, that's our understanding of how to best implement a low error logical qubit has evolved tremendously in the last 15 to 20 years. Just in parallel with better physical implementations, so physicists and engineers, they're getting us better and better qubits and better control. The theorists have figured out ways to do reliable quantum computations with less reliable qubits. So, this is what we needed and this is what we had, and the theorists are lowering the bar in a sense in terms of the kind of experimental control we need, and the experiments are getting better and better and closer to that crossing line, that critical boundary. In some sense, we're crossing that boundary now. That's what's happening right now or over the next small number of years. So, those superconducting qubits I showed you in the first slide, we're probably not going to run Shor's algorithm directly on those qubits. We're going to run them on an array of those qubits. So a few hundred, say, of these qubits is going to encode a small number of logical bits. And these red and blue lines, they just indicate some operations that you're going to do on the qubits near those lines. So there's hundreds, maybe thousands of physical operations to achieve on hundreds of qubits to achieve a controlled knot. That's the state of the art today, which is a lot better than we were 10 years ago. Very elegant, sophisticated mathematical codes with nearest neighbor interactions and so on that allow us to achieve good logical qubits and gates. So another way of looking at it is, what we're going to be talking about mostly at this school is designing algorithms. We're talking about algorithms at the very top layer. Implicitly, when you have a circuit that's, you design an algorithm that says exponentiate this number, you can compile that down to some circuit that actually does the arithmetic. That circuit, that circuit might use all sorts of gates, which are not in your physical, fault-tolerant gate set. You want to compile it down into Hadamards, T's, and C naughts, which we then implement via fault-tolerant code, maybe hundreds of physical bits. And from the bottom layer, you have some physical system, use control sequences to get noisy physical qubits, which are then glued together to create a fault-tolerant logical qubit. So there's a long tool chain that's being developed. So, Anne was asking the question, referring to the question of how far are we implementing a scalable fault-tolerant quantum computer, in particular one capable of threatening modern-day cryptography. So a lot of the metrics you'll hear cryptographers citing today are just not relevant. Okay? Anne mentioned, factoring was implemented, it was factor 15. That's just a demonstration of low-level control. It's actually not really not the metric you should be tracking, how many qubits you have today or what number you factor today. It's really not the relevant thing to be tracking. What you want to look at is how long before we have a scalable, fault-tolerant quantum computer. And once we have that, then you can start tracking how many logical qubits you have, how big of a number, how big of an instance of Shor's algorithm have you implemented on those logical qubits. That's a relevant thing to track. But otherwise, you need to track the metrics relevant to the stage we're at in trying to build a quantum computer. And in the early days, the bottom stage was, let's find some qubits. Let's find some physical qubits. That's stage one. This is a very nice article by Michele Mosca and Robert Schulkoff. The next stage is, let's get multiple qubits interacting and do something with them. The only algorithm, the main algorithm we really need to implement at the physical layer is error correction algorithms, fault-tolerant quantum error correction. The third stage, as I described it, is you can do multiple qubit logic, you can do non-demolition measurements, you can do control and feedback, all the ingredients for doing error correction. Stage 4 is you're doing error correction and you're getting better logical qubit lifetimes than you were with the physical qubits. If you're not, then there's really no point to doing error correction just to get worse performance. But you need all these building blocks. It took 15 to 20 years to achieve stage 1, 2, 3 in superconducting qubits, ion traps, and maybe one or two other implementations. And where experimentalists are today is they're trying to achieve stage 4, which is ultimately the design of a fault-tolerant, scalable qubit. And once you have that, there's a lot of physics going into that, and some engineering as well. And there'll be more and more engineering as we try to scale that up to a large-scale quantum information processing system that will implement non-trivial quantum algorithms. So the important question right now is, how close are we to having a fault-tolerant, scalable design? So it's a lot about meeting these thresholds that the fault tolerance people will talk about. So how close are we to achieving stage 4, where progress continues to go very impressively? In the last year, Google announced its work controlling 9 qubits, and you'll see in the background at the top, the background has this lattice, this array of qubits, with the end game of achieving the surface code, one of these topological codes I was mentioning. And just before this, Delft had a similar experiment with 5x1 sublattice. IBM had a 2x2 sublattice, but they were all trying to implement some kind of topological code that allows for scalable, fault-tolerant quantum computation. So, when I started in the field, I was asked, when do you think we'll have a quantum computer? And certainly, my sense was we're not ready to make those kinds of predictions, but I do think that we'll have about 20 qubits in 20 years, and at that point, we'll have a better clue as to how long this will take. It was largely perceived as a very pessimistic estimate, but I think it's on track. But in the last year, I think we are essentially approaching this 20 qubit regime, which is something you can't brute force. You have to really have achieved some non-trivial amount of control and some serious technologies to be able to do serious things with 20 qubits. So I think if you glue together all the pieces that it'll take to break RSA and say, if things go really well, it could happen as soon as 2026. 1 in 7 chance, so probably not, but maybe. But those odds, I think, increase to about half by 2031. That's my estimate. And shortly after, IARPA announced a program to build a logical qubit, which is one of the key milestones towards a large-scale quantum computer. And very recently, it was announced that IBM, which is one of the groups, one of the front-running groups in this field, was selected for this contract to deliver a logical qubit by early 2021. If they're successful, then how long will it take to scale it up to something that can implement RSA, or can implement Shor's algorithm? Further supporting the thesis that quantum computing is certainly a medium-term threat. It's not some hypothetical, very long-term threat, but something that really we need to take into account now is the NSA's announcement to transition to quantum-resistant algorithms. So related to when will we threaten current cryptography is the question of, well, how many qubits do you need? How big of a quantum computer do you need to break RSA? Is it 100 qubits? Because, for example, our colleagues at Microsoft recently stated, that it's conceivable or possible that have a useful quantum computer within 10 years. But they're referring to having about, I think, on the order of 100 logical qubits to implement certain simulation algorithms. It'll take more than 100 logical qubits to implement Shor's algorithm for 2,000-bit numbers. But how many qubits will it be? Is it a billion? With a trillion gates, say? It's physical qubits. Or a million with 100 million gates? There's a big gap. I mean, there's a lot of time between a system that can control a million qubits to one that can control a billion qubits. So that adds a number of years to the timeline. Is it something else? Right, now the current estimates are somewhere in between here, depending on your assumptions and who's doing the analysis. So we just get a coarse-grained analysis if we just do the heuristic analyses. You do need to get into you need to do a fine-grained analysis of how many qubits does it really take to do this exponentiation, for example. There's a lot of nice work going on in the field of quantum compilation. Martin Rickler is also in the audience. He and his colleagues have been doing a lot of work on this as well. These are some of the examples of the mathematical tools we're using to optimize, often to a great extent, the number of physical gates you need to implement the logical gates. And they not only give us estimates of when Shor's algorithm will work, but any of these other algorithms that we're excited about using to solve important problems. So, those are my background thoughts on quantum algorithms, how soon we'll be able to apply them. I mean, one of the reasons I mention this is when I started in quantum algorithms about 20 years ago, there was a lot of cynicism, like why are you working on algorithms for a computer that will probably never exist? Or at least not in our lifetimes. Like why should a computer science department waste a faculty position on such a thing? And of course, there's all the profound reasons why you should care about quantum information, because even if you can't build a quantum computer, the world is quantum mechanical, so this theory of quantum information is shedding deep insight into the nature of the physical world, as well as the theory of computing. But it's certainly a heck of a lot easier sell if you're going to actually have a quantum computer in the foreseeable future. And I think we're at a stage where we very likely will. We don't know for sure. It's a 50% chance by 2031, that means there's a 50% chance we won't. But I think that the likelihoods are very significant, and the probability goes up a lot shortly after 2031. So how do these quantum algorithms work? Now that I've hopefully motivated the study of quantum algorithms, which to a large extent wasn't necessary because you're all here. So let's start with an analogy to classical randomized algorithms. So I'm using quantum notation to describe strings of bits, but I'm really just talking about classical algorithms here. A very, very trivial example. You start off with 2 bits initialized to 0. You probabilistically evolve to 2 other bits. Could be the same bits, could be different bits with different probabilities. There's some probability of 0, 0 going to 0, 0. Probability 0, 0 becoming 0, 1, and so on. And then you take another step, another randomized step. So after these 2 steps, say, there's 4 paths that take you from 0, 0 to 0, 0. And they each occur with some probability. And the total probability of reaching 0, 0, is just the sum of the probabilities of all the paths taking you to 0, 0. And the probability of a specific path is the product of the probabilities of each step along that path. Basic elementary probability theory, elementary randomized algorithms. So it's a probability of an outcome, and you sum over all the ways to get that outcome, you sum the probability of those events. Now let's suppose instead we run a very similar quantum algorithm where 0, 0 evolves to a superposition of these 4 possibilities. And in the next step, there's another quantum evolution that takes you to the 4 possible outcomes. Similarly, the amplitude of 0, 0 at the end is just the sum of the amplitudes of all the paths that take you to 0, 0. And then if I look at the system at the end, the probability of seeing 0, 0 is its amplitude absolute value squared. So slightly different looking formulas. The basic principles are the same. The total amplitude is just the sum of all the amplitudes of each path taking you to the same place. But then I have to take an absolute value squared. Now, what if I were really curious, and the curiosity was killing me, and I had to know what was the intermediate state. I'm just not happy not knowing. Well, then it collapses, using one of the interpretations of quantum theory. It effectively becomes one of those four states with probability equal to the absolute value squared with the amplitude of that state. If you compute the probability of seeing 0, 0 now, it's slightly different. It's the sum of all the probabilities, the probabilities of each of the paths taking you to 0, 0. You sum all those probabilities, which are the amplitudes squared. So we get an expression that looks very much like the previous one, but what's the main difference between this expression and this expression? The absolute value, initially we took a sum of all these products of amplitudes, we added them up, then we took the absolute value squared. Here we brought the absolute value into the summation and the square inside the summation. Okay, so some probabilities will go up and some will go down. You can easily cook up examples where the probabilities will be much higher in this case, and in other examples where it will be much lower. It's just a different probability distribution. So, you've probably all seen the two-slit experiment, right? It's a classic experiment where if I shoot particles through one of two slits, and if I know which slit it's going through each time, there's a certain probability distribution on the screen. It's just a sum of the probability distribution of if it just goes through one slit, or if it just goes through the other slit. Superpose those two probability distributions, you just take an average of those two, and you get the net probability distribution. That's the classical algorithm. So there's certain areas of the screen which are highly likely, and some which almost never happen. In the quantum case, some of the dark spots become light, and some of the light spots become dark. It's a different probability distribution. So the example I didn't draw up here, for some of the two classical distributions, is very much a classical randomized algorithm. And here's a quantum one. And a quantum computation is very similar. Right? Each spot on this screen is some event, some outcome. In a quantum algorithm, the outcomes are just the configurations of your bit string. And in your classical algorithm, some configurations might occur with high probability and others with low probability. But you run the quantum algorithm and those probabilities change dramatically. And there are certain outcomes where, with any classical interference pattern, you're almost never going to get some magic string, the string you want to find, the factors of your numbers, for example. But with a quantum interference pattern, those events occur with significant probability. So at a high level, quantum algorithms are trying to do is you want to choreograph constructive interference on desirable outcomes and destructive interference on undesirable outcomes. Destructive interference is the reason why in the two-slit experiments, some regions which used to, where the particles used to hit them, when you were observing which slit they went through, suddenly no longer occur. It's because the two paths that go to that one point cancel out. That's destructive interference. Constructive interference is where the two paths going to a point get amplified. They add up in such a way that they're more likely than they were before. So how does the art of quantum algorithmics work? So I'm going to introduce some of the basic tools that have been developed to construct useful quantum algorithms. And then one of my colleagues throughout this week will give you some of the more advanced algorithms, which essentially build on these tools. So Anne has already taught you about the Hadamard basis. So it maps 0 to 0 plus 1, and 1 to 0 minus 1. If you look at the Hadamard matrix, its square is the identity. It's easy to verify that h times h is the identity. So that means if 0 goes to 0 plus 1, 0 plus 1 must go to 0. And it's easy to verify that. by the Hadamard gate, by linearity, 0 goes to whatever 0 is supposed to go to. And 1 goes to whatever 1 goes to. So you get 0 with amplitude a half plus a half. You get 1 with amplitude a half minus a half. Which just gives you 0. This is destructive interference. You get to the 1 state in 2 different ways, except the amplitudes cancel out. And you get to the 0 state in 2 different ways, but they add up constructively. So you get much more than a 1/2 probability of seeing 0, you get a 100% probability of getting 0. So in summary, the Hadamard transformation is a basis change transformation that maps information encoded in the traditional bit into information encoded in a subtle way in the relative phase between 0 and 1. 0 plus 1 is a way of encoding b equals 0, and 0 minus 1 is a way of encoding b equals 1. So it's just a basis change matrix. It's also, in a sense, a Fourier transform. If you take the vector describing b, which is either 1, 0, or 0, 1, and you Fourier transform it, you get 0 plus or minus. You get 1 over root 2 plus or minus 1 over root 2. That's a Fourier transform. We'll often use circuit language to describe gates. So a bit, b is either 0 or 1. You apply the Hadamard gate and you get 0 plus or minus 1. 0 plus 1 if b is 0, and 0 minus 1 if b is 1. Any questions? So if you give me 3 bits, either in 0 or 1, and you apply Hadamard gate to each of these 3 bits independently, you get 3 qubits in the state 0 plus or minus 1. So I've taken 3 bits which I can see, I can measure without disturbing them, and I encode them into the relative phases of these 3 bits. Often it's convenient to, instead of describing the bits as separate bits, let's just say what happens to the bit string, x1, x2, x3. When you apply 3 Hadamard gates to it, you get a superposition of all the strings. What do you get? You see here, if you look at the 3 bits, every 3-bit string occurs with weight 1 over 2 root 2, and then it has a plus or minus sign in front of it. It's either plus 1 or minus 1. And what's the amplitude of, let's try that. 0 plus minus 1, x1, 1. 0 plus minus 1, x2, 1. Sorry, I'm writing this a bit. So you get 3 bits. So clearly we're going to sum over all n-bit strings, all 3-bit strings, y1, y2, y3. There's a 1 over root 2 in front of each of these, so you get 1 over 2 root 2. So what's the amplitude of the specific string y1, y2, y3? So if y1 is 1, so the only way I'm going to pick up a minus sign is if I have a 1 here, right? So y1 has to be 1, to even if there's going to be a minus 1 here. So, but I also need x1 to be 1, because if x1 is 0, this is a plus 1. So I pick up a minus 1 if x1 and y1 are both equal to 1. I pick up another minus 1 if x2 and y2 are equal to 1. And I pick up another minus 1 if x3 and y3 are equal to 1. It's minus 1 to this integer, so I can reduce this. I can also take this modulo 2, of course. And also XOR these 3-bit values. So that's how we get this expression here, where the 3-bit Hadamard transformation takes a 3-bit string, maps into a equal superposition of all 3-bit strings, where the inputs, quantum unitary matrices are reversible, so you don't lose that information about x. So it has to be somewhere, right? And where it is in these relative phases. So each 3-bit string y has a phase in front of it that depends on x. Depends on x and y. So it's minus 1 to the x dot y is the phase in front of y1, y2, y3. We can write this in different terminology. So the string x1, x2, x3 gets mapped to this superposition. Or we can write this as the matrix, which is the tensor product of h with itself 3 times the vector corresponding to x1, x2, x3 is this vector, which is just, again, it's a special kind of Fourier transform. Any questions about this notation? So the Hadamard, the 3-bit Hadamard gate maps, the elementary vectors to these Hadamard states, which are just vectors with pluses and minus 1s corresponding to this inner product. Notice this is not an entangling gate. This is just 3 independent Hadamard gates. It might look like you're entangling stuff, but you're not. This is not an entangled state on the right-hand side. So again, Hadamard is its own inverse. So that means if x1 goes to 0 plus minus 1 to the x1 1, then if somebody hands you this qubit that's an equal superposition of 0 and 1, and hides x1 in that relative phase, and you want to know what that x1 is, don't measure your qubit right away. Apply a Hadamard gate to it, and then you can see what that bit was. If I give you 3 such bits, you can get this 3-bit string out. So if you're somehow handed this 3-bit state, the superposition of all 3-bit strings with a relative phase of minus 1 to the x dot y, in front of string y, the Hadamard gate is the way to decrypt what that string x is. So this is the same thing, but in a different notation. So I think this is actually a good place to stop. Is that a good time, Martha, in terms of lunch? And then we can continue after lunch. I'll introduce some very basic quantum algorithms and show how we can apply them to 3-round Feistel ciphers. We can also take some questions now, actually, before we go for lunch.
Did you thank the speaker?